The name of this video is Energy Discrete Continued. Let us consider a region of space outside this dash boundary the region of space outside this boundary, which I call an infinite boundary, is such that two particles, any pair of particles outside this region effectively do not interact with each other, which means effectively any pair of particles is such that the two particles are at an infinite distance from each other. Similarly, any particle in this region of space is such that it is at infinite distance from any particle in the region below this boundary. The region below the boundary, we call it our laboratory, our lab. That's where we perform our experiments. Let us suppose that we have three point-like charged particles outside the infinite boundary, small q1, small q2, and small q3. They do not interact with each other, they do not interact with anything in our lab. We want to find the electrostatic energy required to bring these three particles to any configuration in our lab. Let us begin with the first particle, Q1. We know that the electrostatic energy and potential are state functions, so we can choose to bring Q1 to a point capital Q1 in our region of space called lab, following any path. For example, this path gamma 1. We could have equivalently followed any other path. When we do that, the question is, what is the work that I had to perform against any electrostatic force to bring Q1 to capital Q1? Obviously, the lab was empty at this point in time, therefore the work required is exactly 0. I don't need to operate against any force to bring it here. There is no resistance against me to do this action. Therefore, in this case, the work due to the external forces for experiment 1, gamma 1, is exactly equal to 0. Now, let us suppose to bring in our lab the particle Q2 to a point capital Q2 in the lab, following any path we want. Let's say this path gamma 2. So in this case, the particle small q1, which is located already at point capital Q1, generates an electrostatic field which is felt by the particle Q2. Therefore, I need to perform a work against the field forces to bring this particle in the lab. In this case, I'm bringing it in the lab at a distance vector r1, 2, which is the distance in vector form between capital Q1 and capital Q2. So in this case, what is the work against the field forces, so the external work in this second experiment, 2? Well, in this case, it's nothing but 1 over 4 pi epsilon naught times the source charge, which is Q1, times the test charge, which is Q2, divided by R12, Colombian type, with normal conditions and infinity. In fact, we started from points which are infinitely away from the point where we end. So that is the work. Finally, suppose that we want to bring in also our third particle, Q3, along any path, gamma 3, to a point capital Q3 at a distance, in this case, this particle feels two electrostatic fields, the one due to Q1 and the one due to Q2. Therefore, there are two distances which we need to take into account. This distance, which is the vector distance R23, and also this distance, which is the vector distance R13. Okay? Therefore, the external work for experiment 3 is going to be the linear superposition of two works. The one against the field due to Q1, 1 over 4 pi epsilon naught, the source, which is Q1, times the test charge, which is Q3, divided by what distance? R13, absolute value. In addition to that, we also have the work, 1 over 4 pi epsilon naught, of the source charge Q2 on the test charge Q3, divided by the distance R23. Great. So now we could proceed and calculate these up to any particle Q capital N. So any generic discrete distribution of particles which we take from infinite distance behind this infinite boundary back into the lab. We bring them into the lab. Okay? So that's what kind of work we need to calculate. This is the procedure we need to follow. Okay, so with this procedure in mind, let us try to generalize this concept a little bit. Okay? So the first thing we notice is that R12, which is the norm of this vector, obviously is the same as R21. And when we generalize this concept, obviously, if we use an index I here, Ri is equal to Rj for any two indices I and j. This is totally true. In addition, we can do the product Q1, Q2, or Q2, Q1. It's abelian. So Qi times Qj is equal to Qj times Qi. It's an abelian property of the product of charges. With this in mind, we can generalize this concept to any discrete distribution by noting that we can rewrite the work in the following fashion. The work due to the against the field forces in general for capital N. Let's start to write it a little bit and then we generalize it with indices. So this is going to be 1 over 4 pi epsilon naught, which is the same for all these works, times Q1, Q2, divided by R12. But now we know that R12 is the same as R21, so why don't we do an artifact and we add Q2, Q1, divided by R21. And we do the same procedure for all these products. So for example, we're going to have Q1, Q3 divided by R13. And let's add Q3, Q1 divided by R31. Obviously, all these quantities, and this we can go on until capital N, same procedure. So obviously, this quantity is equal to this quantity. Similarly, down here, because of these properties up here. Obviously, this is 2 times the work. That is, in order to find the correct result, we need to multiply times 1/2. Okay? That's the artifact. We double it, but then we need to half it in order to get the actual work and not 2 times the work. By means of this simple artifact, we can finally express this work. And I remind you that this work is nothing but the electrostatic energy by definition, UE, for this system of particles, as 1/2 from here, the sum on the first index I, which goes from 1 to capital N, another sum nested into it with index j, which goes from 1 to capital N. Note that I has to be different than j. And here, what we have is simply 1 over 4 pi epsilon naught in a compact fashion, qi, qj divided by rij. So this artifact of doubling all the quantities and multiplying times 1/2 allows us to use indices and find this very compact form of the electrostatic energy. Okay, now I have a question for you for Piazza, and the question is why it has to be that I has to be different than j? Think about that. Instead of answering that question, let us attempt to reshape this function here in a slightly better fashion. So we notice that we can isolate, so we need to remember this factor of 1/2 always. We take this qi, okay, and we isolate it outside so that we want to look at this sum, the sum on j, with I different than j, and 1 over 4 pi epsilon naught qj over rij. So then, if we do that and we take out this 1/2 and qi, we can rewrite this expression for the electrostatic energy, ue, as 1/2, which we should not forget, the sum. So the nested function is on j, so the sum left is on I, on index I from 1 to capital N, of what? Of qi, which we isolated outside, times vi. And what is vi? Let's spell it out one more time here. Is the sum, the only variable left, the only index left is I, so it has to be on j from 1 to capital N, and again, I has to be different than j. Think about that. Of what quantity? 1 over 4 pi epsilon naught times qj, qi is already there, divided by rij. All right. So this is the final expression which I wanted to derive for any arbitrary discrete set of point-like charges in space. This is the electrostatic energy that we get. And so really try to remember this factor of 1/2 that many people tend to forget or don't know where it comes from. It comes from this artifact which allows us to generalize the concept, okay? Not to double count, we need to divide by 2. And it's nothing but the sum of the charge qi times the potential of that charge, okay? With I different than j. All right, so to summarize this video, we generalize the previous video, which was just for 2 point-like charge particles in space, to a set of capital N point-like particles in space with charge, which is q1, q2, etc. until q capital N. We define an infinite boundary outside which all these particles do not interact with each other and do not interact with us in the lab. And then one by one, we bring these particles into the lab and we pay a certain work for each of these actions, gamma 1, gamma 2, gamma 3, for the 3 experiments. We sum them up using an artifact by halving. This allows us to use indices when we generalize to capital N particles, which can be summarized in this form. That's it.